Max Planck's struggle with the mystery of blackbody radiation is one of the most fascinating chapters in the history of science, not because it began with confidence, but because it began with confusion. At the end of the 19th century, physics was supposed to be nearly complete. Many scientists believed the essential laws of nature were already discovered. Only a few small puzzles remained, and blackbody radiation was considered one of those minor issues. Yet this minor issue would eventually shatter classical physics and force the birth of quantum theory. But before that revolution came, it brought years of frustration, failed attempts, and relentless calculations that nearly broke the patience of even a careful thinker like Max Planck. To understand Planck's struggle, imagine the scientific problem he faced. A blackbody is an ideal object that absorbs all radiation that falls on it and emits light only according to its temperature. When heated, it glows red, then orange, yellow, and eventually blue, white at extremely high temperatures. Scientists wanted a theoretical formula to describe exactly how much light is emitted at every wavelength. In laboratories, precise measurements of blackbody spectra were available, and they followed a smooth, predictable curve. But classical physics could not reproduce that curve. Every formula produced by the best physicists of the time either worked beautifully for long wavelengths or matched well at short wavelengths, but none could capture the full span. Worse, one prediction known as the Rayleigh-Jeans law suggested that at high frequencies the energy output should rise to infinity, a physical impossibility. This embarrassing prediction became known as the ultraviolet catastrophe, and it was a direct sign that classical physics had reached its limits. Planck was deeply troubled by this. He was not a rebellious scientist looking to overthrow old ideas. He was a traditionalist who believed in the deterministic foundations of classical physics. His goal was not to build a new theory, but to repair the old one. For years, he worked obsessively, trying to adjust existing equations, introducing new assumptions, and proposing better mathematical descriptions. He treated the problem like a craftsman sanding a rough edge, hoping a smoother version of classical physics would match the data. But every attempt disappointed him. The more he pushed the formulas, the more obvious it became that something fundamental was missing. What made the problem especially painful for Planck was his deep personal belief in the continuity of nature. He saw the laws of thermodynamics and electromagnetism as elegant and complete. The idea that these laws might fail felt almost offensive to him. Yet every night the experimental data stared him in the face, proving that classical physics could not explain the true behavior of radiation. Planck spent long nights calculating, filling pages with equations, trying to invent new mathematical tricks. His work was not guided by physical intuition, but by the desperate hope that a hidden pattern would eventually reveal itself. During these years, Planck often said he felt like he was working in the dark, guided only by mathematical consistency and his faith that nature must be simple at its core. But the path was anything but simple. He gradually realized that no adjustment to classical theory could solve the problem. The failure was not in the surface-level equations, it was in the foundation. This realization did not come as a sudden flash of insight, but as a slow and painful acceptance. Planck described this period as one of the hardest intellectual battles of his life. Each new attempt seemed to create more contradictions, forcing him to reconsider ideas he once believed were unshakable. Finally, after years of struggle, Planck made a decision that even he considered extreme. If classical physics could not reproduce the blackbody spectrum, then classical physics had to be broken. He began to consider a possibility that almost no one else had dared to think. Maybe energy was not continuous. Maybe it came in discrete, tiny packets. This idea went against everything he had been taught. But the mathematics demanded it, and Planck believed that when the math and the data agreed, nature must be speaking through them. So he followed the numbers, even though they led him into unfamiliar territory. Planck introduced the revolutionary idea that energy is emitted in fixed amounts, proportional to a constant value that would later bear his name. With this single assumption, he derived a formula that matched the experimental curve perfectly. After years of failure, the solution appeared almost like a miracle. Yet even then, Planck struggled to accept the deeper meaning of his discovery. He had solved the Blackbody problem, but he had created a new mystery. Why should nature operate in discrete steps? The world would later celebrate this moment as the birth of quantum theory, but at the time, Planck saw it simply as the only way to make the equations work. His struggle with Blackbody radiation was not just a scientific challenge. It was an emotional battle between loyalty to classical physics and the undeniable truth revealed by experimental data. Through persistence, humility, and mathematical courage, Planck solved a mystery that had defeated the greatest physicists of his time. And in doing so, he unknowingly set the stage for a new era of science. In the late 19th century, classical physics was believed to be unshakable. Scientists were convinced that the laws discovered by Newton, Maxwell, and Boltzmann could explain every natural phenomenon. The world seemed orderly, predictable, and mathematically complete. Yet hidden inside the glow of heated objects was a problem that quietly resisted every classical explanation. It was the mystery of energy emission at different wavelengths, a puzzle so small it was at first ignored, but so deep it would eventually break the entire foundation of classical physics. The failure of classical theory to explain how objects radiate energy became one of the most dramatic turning points in scientific history. The issue began with something seemingly simple. When you heat an object, it glows. First a faint red, then brighter, then shifting toward yellow and white as the temperature rises. This glow, called thermal radiation or Blackbody radiation, follows a very specific pattern. Physicists had measured this pattern in laboratories with great accuracy. It wasn't random, it had structure, smooth transitions, and precise peaks. Nature was clearly following a law. But the laws known at the time couldn't describe it. Classical physics attempted to use electromagnetism and thermodynamics to predict how much energy a heated object emits at each wavelength. At long wavelengths, these laws seemed to work reasonably well, but at short wavelengths, the predictions broke down completely. The Rayleigh-Jeans law, derived from classical assumptions, suggested that as wavelength decreased, the emitted energy should increase without limit. This meant that a heated object should release infinite energy in the ultraviolet range, a physical impossibility. No object in the universe behaves that way, yet classical theory insisted it must. This contradiction became known as the ultraviolet catastrophe, and it stood as a glaring sign that something was fundamentally wrong. The term catastrophe wasn't an exaggeration. It showed that classical physics, which had explained planets, electricity, magnetism, and motion, suddenly collapsed when faced with something as simple as the glow of a hot object. No amount of adjusting constants or tweaking equations could fix it. The failure wasn't a small error in calculation. It was a complete structural breakdown of the classical worldview. Physicists knew the experimental data was correct. They had precise curves showing how radiation intensity changes with wavelength. However, every classical model either matched one part of the curve while failing elsewhere, or produced shapes that looked nothing like the real spectrum. Some formulas captured low-frequency behavior but exploded unrealistically at high frequencies. Others matched the high-frequency end but failed at the lower frequencies. Nature refused to fit inside any classical box. This situation created a sense of intellectual crisis. Classical physics had always assumed that energy could vary smoothly, like water flowing from a tap. It imagined that atoms and oscillators inside a hot object could emit any amount of energy, large, small, or somewhere in between. This assumption seemed obvious, almost impossible to doubt. But that assumption was also the reason classical physics failed so dramatically. By allowing energy to be unrestricted and continuous, classical theory predicted infinite emission at short wavelengths. The failure was not a minor flaw, but a fundamental contradiction between theory and reality. In universities and laboratories, this problem haunted physicists. They had built their careers on the reliability of classical laws, and now those laws were being challenged by a simple glowing object. For decades, no one could make sense of it. Some scientists speculated that there might be unknown limits inside matter. Others hoped that an adjustment to statistical mechanics could solve everything. But each attempt ended in disappointment. Classical physics was trapped by its own assumptions. The failure became even more striking when researchers plotted the experimental data. The Blackbody curve had a clear peak that shifted with temperature, and its shape followed a distinctive pattern. Classical theory could not reproduce this shape. For every temperature and every wavelength, something was wrong. The deeper physicists pushed classical equations. The more they realized the problem was not with the math, but with the foundational belief that energy behaved continuously. This realization created an atmosphere of scientific tension. The pillars of physics seemed to wobble. If classical laws couldn't explain something as ordinary as heat radiation, what else might they fail to describe? The mystery of energy emission at different wavelengths was like a small crack at the base of a dam, slowly revealing the pressure of a much larger problem. Yet no one at the time imagined that solving this puzzle would require tearing physics apart and rebuilding it in an entirely new way. As the 19th century came to a close, scientists began to accept the harsh truth. Classical physics was incomplete. It could not penetrate the microscopic world. It could not describe the behavior of atoms or the true nature of energy. Something new was needed, something that would challenge old beliefs and reshape scientific understanding. But no one knew what that new idea could be. It was in this atmosphere of uncertainty that Max Planck entered the scene. Planck's eventual solution would revolutionize physics. But the reason his idea was needed at all was because classical physics had failed completely and undeniably. The glow of a heated object, once considered a simple curiosity, became the trigger for a scientific revolution. And the failure of classical physics to explain energy emission at different wavelengths marked the beginning of the quantum era, a moment when human understanding of nature changed forever. At the end of the 19th century, physics rested on a deep and comforting belief. Nature was continuous. Everything, from the motion of planets to the flow of electricity, was thought to occur smoothly, without breaks or jumps. Energy, in particular, was assumed to behave like a fluid that could be divided endlessly. This belief was so fundamental that scientists rarely questioned it. But when Max Planck stepped into the puzzle of Blackbody radiation, he found himself forced to suggest something unthinkable: that energy might not be continuous at all. It might come in discrete, tiny packets, each one separated from the next by a fixed amount. This idea would become the seed of quantum theory, but at the moment Planck proposed it, it was nothing short of shocking. Planck never wanted to challenge the foundations of physics. In fact, he admired classical theory and believed deeply in its continuity and elegance. But the mathematical battle he fought against the Blackbody problem offered no mercy. Every attempt to fix the equations with classical assumptions ended in contradictions. The ultraviolet catastrophe stood like a wall that no classical idea could break through. Nature seemed to whisper a truth that the old theories refused to hear. In this corner of physics, continuity no longer described reality. Planck searched desperately for a way out. He considered every known rule of electromagnetism and thermodynamics, adjusting parameters, reshaping equations, and pushing familiar principles to their limits. Yet the problem remained stubborn. The data curve of Blackbody radiation was precise and undeniable, and Planck's mission was to match it. But the closer he looked, the more he sensed that the problem wasn't in the details. It was in the very assumption that energy flowed continuously. Something had to give. It was in this moment of intellectual pressure that Planck did the one thing he never expected to do. He made a mathematical gamble. Instead of assuming that oscillators inside a heated object could take on any value of energy, he proposed they could only have energies that were multiples of a minimum amount. This smallest chunk of energy depended on the frequency of the radiation and a new constant that Planck introduced into his formula. With this single bold step, energy became quantized. The idea sounds simple in hindsight, but at the time it was like telling the scientific world that the smoothness of reality was an illusion. According to Planck, an oscillator could not release any arbitrary amount of energy. It could only emit energy in specific, fixed-sized packets quanta. This meant nature operated in steps, not in a continuous flow. Imagine climbing a staircase rather than walking up a ramp. Each step is separated. You cannot stand halfway between one quantum and the next. This was the essence of Planck's radical idea. When Planck used this assumption to calculate the Blackbody spectrum, the result was astonishing. The formula matched the data perfectly across all wavelengths. The ultraviolet catastrophe vanished. The curve fell into place with beautiful precision. Planck had solved the problem that had haunted physicists for decades. But the meaning of what he had done was far greater than one formula. He had accidentally broken the deepest assumption of classical physics. Planck himself hesitated to accept the full implications of his idea. For him, quantization was initially a mathematical trick, a step he took reluctantly because it worked, not because he believed energy was truly discrete. But the more he studied the consequences, the more he realized that the structure of nature might genuinely be quantized. The universe, at its smallest scales, might be built from packets rather than continuous flows. This was a revolutionary thought, one that placed Planck on the boundary between two eras, the age of classical certainty and the soon-to-emerge quantum world. The radical nature of Planck's proposal can only be understood by imagining how scientists of the time viewed energy. To them, energy was like water in a river, smooth, uninterrupted, infinitely divisible. Planck's quanta turned that river into a series of droplets. It suggested that light, heat, and radiation did not behave like continuous waves, but were made of discrete bits. This idea violated intuition and clashed with the philosophical beliefs of many leading physicists. Yet it worked. It explained what classical theory could not. In the years that followed, the scientific community struggled to accept Planck's concept. Many dismissed it as a strange mathematical convenience, useful but not fundamental. Even Planck hoped that someone would reinterpret his formula in a continuous framework. But the tide had already turned. Einstein soon expanded Planck's idea to explain the photoelectric effect, showing that light itself behaved as if it was made of particles photons. Suddenly, Planck's quanta were no longer mathematical artifacts. They were real features of nature. Planck's introduction of energy quantization did not just fix a theoretical problem. It opened a doorway into a new realm of physics where electrons jump between energy levels, where particles behave as waves, and where certainty dissolves into probability. The quantum world was born from the moment Planck proposed that energy is not continuous. His radical idea became the cornerstone of one of the most powerful and accurate scientific theories in history. What began as a reluctant adjustment to match experimental data became a revolution that reshaped human understanding of matter, energy, and reality itself. Max Planck, the man who never set out to challenge classical physics, became the pioneer of quantum theory, all because he dared to suggest that the smoothness of energy was an illusion and that the universe, at its core, ticks forward in tiny, indivisible steps. When Max Planck introduced the idea that energy comes in small, fixed packets called quanta, he was not merely adjusting an equation. He was redefining the structure of reality. To understand the magnitude of this step, imagine a world where everything appears smooth and continuous, water flowing without interruption, light spreading seamlessly across space, heat rising gradually from a flame. Classical physics had always assumed that this smoothness extended all the way down to the microscopic level. Energy, according to that world view, could be divided endlessly. But Planck, working quietly at the turn of the 20th century, found himself face with a truth that shattered that belief. Nature does not always operate smoothly. Sometimes it moves in tiny leaps. His insight began with a mathematical desperation. The Blackbody radiation problem had resisted every classical attempt to explain it. The experimental data demanded a formula with a specific shape, one that dipped at low frequencies, rose to a peak, and then dropped sharply at higher frequencies. Classical physics could not produce such a curve without falling into contradictions. Planck faced a challenge that seemed impossible to solve within the boundaries of traditional ideas. He needed a completely new assumption, something bold enough to break the deadlock. In this moment of intellectual crisis, Planck made a proposal that would transform physics. He suggested that the oscillators inside a heated object, tiny vibrating sources of radiation, could not take on just any amount of energy. Instead, they were restricted to fixed levels. They could emit or absorb energy only in whole number multiples of a basic unit. This smallest unit, which he called energy element, was later named the quantum. Planck's equation stated that the energy of each quantum was proportional to the frequency of the radiation, and the constant of proportionality was the now famous Planck constant, a number that would become one of the pillars of quantum physics. This proposition may sound straightforward today, but at the time it was extraordinary. It suggested that energy is granular. Instead of being like a smooth stream, energy was more like a string of beads, separate, countable, indivisible. A glowing object did not emit energy continuously. It released it in discrete bursts. These bursts, or quanta, were incredibly tiny, far too small to detect directly, but large enough to change the mathematics of radiation completely. When Planck inserted this idea into his calculations, the results were astonishing. The formula matched the Blackbody spectrum perfectly from one end to the other. What classical physics had failed to explain for decades was suddenly clarified by the simple yet radical notion of quantized energy. The shape of the curve, the disappearance of the ultraviolet catastrophe, and the alignment with experimental data all came together in one elegant solution. Nature, it seemed, behaved exactly as Planck's quanta required. Yet Planck himself viewed the idea with caution. He was a conservative physicist by temperament, and the idea of quantized energy felt like a rebellion against everything he had studied. He introduced it because the mathematics demanded it, not because he wanted to abandon classical thinking. But once the concept was out, it began to grow beyond his initial expectations. Other scientists realized that Planck's quanta were not just useful for Blackbody radiation. They revealed something deeper about the universe. To visualize Planck's idea, imagine a staircase instead of a ramp. On a ramp, you can stand anywhere, halfway up, 3/5 of the way, or any point in between. That is the classical view of energy, smooth and continuous. On a staircase, you can only stand on the steps. You cannot stand between them. Energy levels in Planck's model worked the same way. An oscillator could only occupy specific steps, and each step required a fixed amount of energy called a quantum. This idea, which seemed almost absurd at first, soon became the foundation for understanding electrons in atoms, photons of light, and the behavior of matter on the smallest scales. The introduction of quanta opened the door for Einstein to propose that light itself is made of particles, photons, each carrying a quantum of energy. It allowed Niels Bohr to explain how electrons jump between specific energy levels within atoms. It led to the discovery of wave-particle duality, the uncertainty principle, and the entire field of quantum mechanics. All of these developments trace back to one moment, when Planck proposed that energy comes in fixed packets. The impact of Planck's quanta extends far beyond theoretical physics. Today, the devices that shape modern technology, lasers, LEDs, MRI machines, atomic clocks, semiconductors, and even the digital cameras inside smartphones, depend entirely on the quantized nature of energy. Without Planck's insight, the technological world we inhabit would not exist. But the true significance of Planck's proposal lies not only in its applications, but in its philosophical implications. It challenged humanity's deepest assumption about the universe. It showed that at the smallest scales, reality is not smooth but grainy, not continuous but discrete. The universe jumps, it pulses, it exchanges energy in tiny bursts. Planck's quanta revealed a hidden structure beneath the surface of reality, a world where the rules are unfamiliar, counterintuitive, and profoundly beautiful. What began as a mathematical necessity became a revolution. Max Planck's proposal that energy comes in small, fixed packets reshaped the very meaning of physical law. It marked the birth of quantum theory and changed the direction of science forever. When Max Planck introduced the concept of quantized energy, he did more than solve a stubborn problem in thermal radiation. He uncovered a new constant of nature, a number so fundamental that it would become one of the cornerstones of modern physics. This constant, which the world would come to know as Planck's constant, represented something entirely new, something that classical physics had never imagined. It was not simply another value to plug into equations. It was a key that unlocked a hidden layer of reality, a symbol of the quantum world that lay beneath the smooth and predictable surface of everyday experience. To understand the significance of this constant, we must go back to the moment when Planck was struggling with the Blackbody radiation problem. His equations were failing, classical physics was failing, the spectrum curve from experimental data refused to bend to any existing theory. Planck had reached a point where mathematics alone could no longer rely on traditional assumptions. He needed something new, something that would break the continuous flow of energy into discrete steps. In making this bold move, Planck discovered something extraordinary. The energy of each quantum, he proposed, was proportional to the frequency of the radiation. This meant that high-frequency radiation carried larger packets of energy than low-frequency radiation. The proportionality factor, the number that connected frequency to energy, was a constant that had never appeared in physics before. Planck denoted it by the letter H, a simple symbol for an idea that would change everything. It was a tiny value, unimaginably small in everyday terms, but that smallness concealed its universal importance. This constant set the scale at which quantum effects become noticeable. It defined the size of each quantum, the smallest indivisible unit of energy exchange. At the time, Planck did not know what deep meaning this constant held. He introduced it because the mathematics required it. Without H, the curve would not match the data. But the constant itself represented something far more profound than a mathematical correction. It indicated that nature has a fundamental graininess. The world is not infinitely divisible. It is stitched together by steps so tiny that only at the atomic level do they become essential. Planck's constant became the first doorway into the quantum universe. Every photon, every atomic transition, every electron orbit inside an atom obeys rules written around this constant. Without Planck's H, electrons would collapse into atomic nuclei, atoms would not exist, and matter as we know it would be impossible. The constant defines the discreteness of energy, the rhythm of quantum jumps, and the boundary between classical behavior and quantum behavior. At the dawn of the 20th century, this idea seemed almost unbelievable. How could one constant, one tiny number, play such an important role? Yet history soon proved Planck's intuition right. In 1905, Einstein used Planck's constant to explain the photoelectric effect, showing that light itself is composed of particles photons, each carrying an energy of h times its frequency. A few years later, Niels Bohr used H to describe how electrons occupy discrete orbits within atoms. Later still, the constant became central to Schrödinger's wave equation, Heisenberg's uncertainty principle, and the entire development of quantum mechanics. Everywhere that quantum theory appears, Planck's constant follows. It acts like a signature, a mark of the quantum world. It tells physicists where classical ideas end and quantum rules begin. The size of H determines how large quantum effects are. In everyday life, cars, planets, apples, the constant is so small that quantum jumps are invisible, drowned out by large-scale behavior. But in atoms and subatomic particles, its presence dominates everything. This explains why the world feels continuous at human scales, but becomes strange and discrete when examined closely. Planck's constant is now recognized as one of the fundamental constants of nature, alongside the speed of light and the gravitational constant. It is woven into the fabric of physical law. Without it, there would be no quantum mechanics, no understanding of atomic structure, no prediction of chemical behavior, and no advancement in modern technologies like lasers, semiconductors, MRI machines, and atomic clocks. All of these rely directly on Planck's constant. The constant also reshaped the philosophical understanding of the universe. Before Planck, scientists believed the laws of nature were continuous and deterministic. After Planck, they realized that the world is built from jumps, quantum leaps governed by a fundamental boundary. The presence of H meant that nature had limits, minimum amounts, smallest possible values. It marked the end of the idea that energy, momentum, or action could change smoothly without restriction. This constant told humanity that the universe is both predictable and unpredictable, orderly and grainy at the same time. As quantum physics matured, Planck's constant became not just a number, but a symbol of a new reality. It represented a frontier where classical intuition fails, and where the true structure of the universe reveals itself. It is a reminder that the universe is far more intricate than it appears, and that even the smallest constant can point the way to the deepest truths. Planck introduced H reluctantly, never imagining it would revolutionize science. Yet that tiny constant became one of the most important discoveries in the history of physics. It marked the birth of the quantum age, an invisible but powerful sign that the universe is built on quanta, small, fixed packets of energy that obey the laws of Planck's constant. In the silent depths of the universe, long before stars were born and galaxies formed their spirals, a profound dance was already taking place, an exchange so delicate and yet so powerful that it would determine the behavior of every atom, every ray of light, and every phenomenon that would follow. This is the story of how atoms and radiation communicate, how they give and take energy, and how this invisible dialogue shapes the very fabric of reality. Every atom in existence is a tiny world of its own, built around a nucleus and surrounded by electrons. These electrons do not move freely. Instead, they occupy specific layers or energy levels, like rungs on a cosmic ladder. They cannot simply float between levels whenever they want. They must obey the strict rules written by nature, a script defined by quantum mechanics. According to this script, an electron can only rise or fall between these levels if it exchanges a precise amount of energy. Not more, not less. And this exact energy arrives or departs in the form of radiation. Radiation, whether we call it light, photons, electromagnetic waves, or simply energy, is the messenger of the universe. It carries information, momentum, and energy from one place to another. When such a photon encounters an atom, a remarkable moment unfolds. If the photon's energy matches the gap between two electron levels, the atom can absorb it. This absorption is not random. It is one of the most selective processes in nature. Only the right photon, with the right energy at the right moment, can persuade an electron to jump. When absorption happens, the atom is transformed. The electron leaps to a higher energy level, creating what scientists call an excited state. But this excited state is temporary, fragile, almost restless. The atom cannot hold this borrowed energy for long. Eventually, the electron must return to its original position. When it falls back, the atom releases a photon, sending the energy back into the universe in a flash of light. This process is known as emission, and it is one of the most fundamental actions in physics. This simple cycle, absorption and emission, creates some of the most beautiful and important phenomena in the cosmos. It explains why gases glow when excited, why stars shine with incredible brightness, and why the atoms in our bodies interact with the world around us. Each photon absorbed or emitted leaves behind a signature, a fingerprint of energy that reveals the quantum structure of the atom. But this exchange is not merely a mechanical transaction. It is the foundation of communication in the universe. When the atoms in a star absorb and emit photons, the star's light changes color. These changes travel across millions of light years, carrying clues about the star's temperature, composition, age, and life cycle. Astronomers reading this light are essentially listening to the whispers of atoms from across the cosmos, messages written in energy. Closer to home, energy exchange defines the behavior of everything from the screens we look at to the chemical reactions that sustain life. When sunlight touches a leaf, photons are absorbed by specialized molecules, triggering electron jumps that fuel photosynthesis. When a microwave heats food, it sends radiation that makes water molecules vibrate, transferring energy throughout the meal. Even our ability to see depends entirely on this exchange. Photons enter the eye and strike molecules in the retina, which then shift their structure and send signals to the brain. Without this atomic conversation, vision would not exist. Behind this exchange lies an even deeper principle: quantization. Energy in the atomic world is not continuous. It comes in small, indivisible packets. This idea, first proposed by Max Planck and later expanded into the foundation of quantum mechanics, changed science forever. It explained why atoms do not collapse, why light behaves both like a wave and a particle, and why matter interacts with energy in steps rather than smooth flows. Every electron jump, every photon emitted, every beam of light we see is a testament to this quantized world. Yet, for all its precision, energy exchange between atoms and radiation also introduces randomness into the universe. We cannot predict exactly when an excited atom will emit a photon or precisely which direction that photon will travel. This element of unpredictability gives rise to the probabilistic nature of quantum mechanics, a system where certainty is replaced by likelihood, where nature chooses among possibilities instead of following strict determinism. As we zoom out from the microscopic realm to the grand scale of galaxies, we begin to see how these tiny exchanges define the large-scale structure of everything. Clouds of gas in space absorb and emit radiation, creating the glowing nebulae that decorate the cosmos. Stars form when atoms collapse under gravity, heating until energy exchange becomes intense enough to ignite nuclear fusion. Entire galaxies shine with the combined output of trillions of atoms interacting with radiation every second. On Earth, our technology harnesses this same exchange. Lasers operate by forcing atoms into excited states and then triggering them to emit photons in perfect synchrony. Solar cells capture photons from sunlight and convert their energy into electrical current. Fiber optic communication uses light to carry information across continents. All of it depends on the atomic exchange of energy that has been occurring since the dawn of time. The story of energy exchange between atoms and radiation is not just a story of physics. It is the story of how the universe interacts with itself. It is the conversation between light and matter, the interplay that governs everything from the glow of neon signs to the birth of stars. It is nature's silent dialogue, timeless and universal, shaping the world we see and the worlds we can only imagine. In the vast expanse of the universe, among countless elements and cosmic mysteries, one atom stands as the simplest, the lightest, and yet one of the most profound teachers in the history of science. Hydrogen, just one proton and one electron, holds secrets that transformed our understanding of reality. Its simplicity became a window into the strange world of quantum mechanics, revealing rules that no one had imagined before. This is the story of how the universe's smallest building block exposed the deepest truths about matter, energy, and the nature of existence. For centuries, hydrogen seemed unremarkable, a tiny, invisible gas, common in the stars, ordinary in its appearance. But hidden within this ordinary atom was a pattern so exact, so beautiful, that decoding it required a completely new way of thinking. When hydrogen gas is heated or excited, it glows with specific colors, not a continuous rainbow, but a series of sharp lines, each representing light of a very particular wavelength. These lines, known as the hydrogen spectrum, appeared like cosmic fingerprints. Scientists stared at these lines, puzzled by their precision. They wanted to know, why only these colors? Why did hydrogen emit light in such strict patterns, as if following a secret code? The answer did not lie in classical physics. No simple idea could explain why an atom would release energy only in certain amounts. It took the bold mind of Niels Bohr to propose a radical idea. Electrons do not orbit freely. They occupy specific energy levels, and they can move between these levels only by absorbing or emitting exact packets of energy. These packets were not theoretical. They were the very photons that created the mysterious lines in hydrogen's spectrum. Suddenly, the atom was no longer a miniature solar system. It was a quantum machine operating in jumps, steps, and discrete transitions. With hydrogen, Bohr cracked open the door to the quantum world. Yet, the hydrogen atom held even more secrets. When scientists examined the spacing of its spectral lines, they realized these were not random. They followed a mathematical pattern. Johann Balmer, a Swiss schoolteacher, discovered a simple formula that predicted the wavelengths of visible hydrogen lines. That formula was later understood as a reflection of the electron's energy structure inside the atom. It was as if hydrogen had written its own rules in light, waiting patiently for humanity to decode them. Bohr's model explained the first layer of hydrogen's mystery, but as experimental techniques improved, scientists detected tiny shifts, fine details, and unexpected splits in the spectral lines. The atom was more complex than originally thought. These small deviations hinted at deeper principles that would eventually lead to the full development of quantum mechanics. Werner Heisenberg introduced the uncertainty principle. Erwin Schrödinger created wave mechanics. Together, these ideas revealed that the electron in hydrogen was not a small particle orbiting a nucleus, but a wave, a cloud of probability existing everywhere at once until measured. Hydrogen was not a bead on a wire, it was a symphony of possibilities. As this new understanding spread, it reshaped physics. The hydrogen atom became both a puzzle and a proving ground. Every theory had to match the spectral lines of hydrogen. If it failed, the theory was rejected. Hydrogen became the ultimate test of truth in the quantum world. And remarkably, the quantum rules derived from hydrogen did not just describe atoms, they described nature itself. From the behavior of electrons in metals to the stability of stars, quantum mechanics, born from the secrets of hydrogen, became the foundation of modern science. Beyond the laboratory, hydrogen's quantum nature tells the story of the cosmos. When stars form, hydrogen atoms are crushed together under immense gravitational pressure, igniting nuclear fusion. In that moment, hydrogen transforms into helium, releasing the energy that powers the sun and every star in the night sky. This fusion process follows quantum rules, allowing particles to tunnel through barriers that classical physics says they should never cross. Without this quantum tunneling, the universe would be dark and cold. Every sunrise, every star we see, every galaxy glowing across the void owes its existence to the quantum behavior of hydrogen. Even the colors of the universe come from hydrogen. The beautiful red emission of the Balmer Alpha line paints the glowing nebulae that decorate the night sky. Radio telescopes detect the 21-centimeter hydrogen line, a signal emitted when the electron in hydrogen flips its spin. This single transition has allowed astronomers to map the structure of the Milky Way, revealing its arms, its rotation, and its hidden clouds of gas. Hydrogen, the simplest atom, has become the narrator of cosmic history. On a deeper level, hydrogen also explains why matter is stable. The interaction between its electron and proton follows quantum rules so precisely that it creates a stable structure, one that does not collapse and does not explode. This stability allows atoms, molecules, and life itself to exist. The same principles apply to every atom in your body: carbon, oxygen, nitrogen, calcium. All of them follow the quantum lessons first discovered in hydrogen. Hydrogen taught humanity that the universe is not what it seems. Beneath the smooth surface of everyday experience lies a world of probabilities, discrete energies, mathematical beauty, and profound simplicity. A world where particles behave like waves, where energy comes in packets, and where the smallest atom can illuminate the grandest mysteries. From the glowing stars above to the chemistry of life, everything traces its origin back to the secrets hidden inside hydrogen. What began as a puzzle of colored lines became a revolution in science. And though hydrogen is just one proton and one electron, it remains a guide, a reminder that even the simplest things can hold the deepest truths. The universe speaks softly through its smallest building block, and those who listen discover the quantum heartbeat of reality itself. Max Planck was a PL, a man N of CK, was a man of intellect, meticulous reasoning, and a profound respect for the established laws of physics. He lived in an era when the world of science seemed almost complete. Classical physics, with its elegant equations and predictable principles, had explained everything from planetary motion to the behavior of gases. Nature was orderly, continuous, and, above all, comprehensible. And yet, in the midst of this apparent perfection, Planck encountered a problem that classical physics could not solve: the mystery of blackbody radiation. For years, he wrestled with equations that stubbornly refused to align with experimental data. It was a puzzle that demanded an entirely new way of thinking, one that he approached with both caution and awe. After relentless calculation, experimentation, and analysis, Planck proposed a radical solution. Energy is not continuous, but comes in discrete packets, which he called quanta. This idea, which today forms the foundation of quantum mechanics, was nothing short of revolutionary. Classical physics had assumed that energy could flow in an uninterrupted stream, like water pouring from a tap. Planck's concept suggested instead that energy is exchanged in tiny, indivisible amounts. For most physicists, this was astonishing. It overturned centuries of assumptions about the smoothness and predictability of nature. But for Planck himself, the idea was even more unsettling than for others. Planck did not immediately embrace the philosophical implications of quantized energy. To him, the quanta were, at first, a mathematical convenience, a tool to make the numbers work. He was primarily concerned with fitting the experimental data, not with rewriting the laws of physics. The equations aligned perfectly when he assumed energy was discrete, and the ultraviolet catastrophe vanished. Yet Planck hesitated to claim that the universe itself actually obeyed this rule. He remained loyal to classical ideas in his thinking, cautious about attributing physical reality to a concept that contradicted centuries of scientific understanding. In his own mind, quantization was a provisional step, a bridge over a gap in the equations rather than a statement about nature's true structure. This reluctance highlights Planck's remarkable scientific character. He was not a revolutionary eager to overthrow tradition. He was a careful, disciplined thinker committed to truth, even when truth demanded uncomfortable concessions. His hesitation reveals a scientist at a crossroads caught between the certainty of classical laws and the strange new world his own calculations were revealing. He had opened a door into the quantum realm, but was hesitant to step fully through it, aware that doing so would challenge the very foundations of physics as he knew it. Even as the implications of his theory began to spread, Planck maintained a cautious distance from its philosophical consequences. He spoke of quanta as a necessary assumption for solving the Blackbody problem, rather than a reflection of physical reality. Other scientists, including Einstein, would later take the idea further, applying it to light, electrons, and the photoelectric effect, embracing the full scope of its meaning. Planck, by contrast, remained a conservative figure, concerned primarily with the correctness of his formulas. This subtle distinction between discovering a tool and recognizing a fundamental truth is what makes Planck's story so compelling. It reminds us that scientific breakthroughs often arrive incrementally, with even their inventors taking time to grasp the full magnitude. Planck's initial disbelief also illustrates the tension between mathematical success and physical intuition. The equations he produced worked flawlessly. They matched experiment, explained the previously inexplicable, and resolved contradictions that had plagued physicists for decades. And yet, the reality implied by the maths, that energy is inherently quantized, felt almost heretical to the trained mind of a physicist raised in the era of continuity and determinism. Planck's caution exemplifies the humility and rigor of a scientist unwilling to declare a revolutionary truth without certainty, even when the evidence was staring him in the face. Over time, the deeper meaning of quantization became unavoidable. As Einstein applied Planck's concept to explain the photoelectric effect, and as Niels Bohr constructed his model of the atom based on discrete energy levels, the reality of quanta could no longer be dismissed. Planck gradually accepted that his mathematical trick reflected a genuine feature of the universe. But this acceptance came slowly and with reflection, underscoring that even brilliant minds can hesitate before embracing ideas that challenge deeply ingrained paradigms. Planck's initial reluctance did not diminish his role as the father of quantum theory. On the contrary, it humanizes him, showing that groundbreaking discoveries often emerge from a careful dialogue between intuition, calculation, and evidence. His hesitation reminds us that scientific progress is rarely instantaneous. It unfolds through meticulous reasoning, repeated testing, and gradual recognition of truths that may initially seem implausible. The story of Planck's partial disbelief in the significance of his own theory is a testament to the cautious courage of a great scientist. He ventured into uncharted territory, proposed a revolutionary idea, yet maintained a disciplined skepticism. Only time, further experimentation, and the work of other pioneering physicists revealed the full depth and importance of his discovery. Planck's journey illustrates the delicate balance between innovation and prudence, between mathematical insight and physical understanding, that lies at the heart of all true scientific achievement. At the dawn of the 20th century, the nature of light was one of the most perplexing questions in physics. Scientists had long debated whether light was a wave, spreading continuously like ripples across a pond, or a particle, consisting of discrete bullets traveling through space. Experiments with reflection, refraction, and diffraction seemed to confirm the wave theory. Yet, when it came to the phenomenon now known as the photoelectric effect, waves alone could not explain the observations. Metals exposed to light would emit electrons, but only if the light reached a certain frequency. Increasing the brightness of light below that threshold frequency produced no electrons at all, no matter how intense the light. This contradiction puzzled the scientific community and defied classical theory. It was in this context that Albert Einstein turned to the revolutionary idea introduced by Max Planck just a few years earlier. Planck had suggested that energy is quantized, emitted in small, discrete packets called quanta. At first, Planck had introduced the idea reluctantly, primarily as a mathematical fix to the problem of blackbody radiation, without fully accepting that energy truly behaved in discrete amounts. But Einstein saw a deeper potential. He realized that if light itself consisted of discrete packets later called photons, then many puzzling observations about energy exchange could suddenly make sense. Each photon would carry a fixed amount of energy, proportional to its frequency, exactly as Planck had proposed for oscillators in matter. Einstein applied this concept to the photoelectric effect with remarkable insight. He proposed that when a photon strikes an electron in a metal, it transfers its energy directly to that electron. If the photon's energy exceeds a specific threshold, the electron is ejected from the metal surface. If the photon's energy is below the threshold, no electron is emitted, regardless of how many photons strike the surface. This simple idea explained the experimental facts perfectly. It was not the intensity of light that mattered, as classical wave theory would suggest, but the energy of each individual quantum of light. Einstein had used Planck's quantum hypothesis to unlock the behavior of electrons under illumination, revealing that light itself must have particle-like properties. The implications of this were profound. For centuries, light had been treated purely as a wave, with phenomena like diffraction and interference seemingly incompatible with the concept of particles. Yet Einstein's work demonstrated that light could exhibit both wave-like and particle-like behavior depending on how it was observed. This dual nature of light became one of the foundational principles of quantum physics, fundamentally changing our understanding of the nature of energy, matter, and observation itself. Einstein's explanation of the photoelectric effect was not merely theoretical speculation. It made clear, testable predictions. For example, increasing the intensity of light above the threshold frequency should increase the number of emitted electrons, but not their individual energy. Conversely, changing the frequency of light would change the energy of the emitted electrons, but not their number. Experiments conducted shortly thereafter confirmed these predictions with stunning precision. Suddenly, a mysterious phenomenon that had defied classical physics for decades was fully understood through the application of Planck's quantum idea. This breakthrough earned Einstein the Nobel Prize in Physics in 1921, not for relativity, but specifically for his explanation of the photoelectric effect. It represented a crucial step in the acceptance of quantum theory, showing that Planck's concept of energy, quanta, was not a mathematical curiosity, but a fundamental feature of the universe. Energy is not infinitely divisible. It is carried and transferred in discrete amounts, and light itself is composed of these packets. The implications extended far beyond photoemission, touching the behavior of atoms, molecules, and the very principles that govern chemistry and electronics. Technologically, Einstein's insight laid the foundation for innovations that would transform the modern world. Solar panels, photodetectors, and countless other devices rely directly on the principles of the photoelectric effect. Every time sunlight is converted into electricity, every camera sensor responds to photons, every light meter measures intensity, it is Einstein's application of Planck's quanta that makes the process possible. The practical ramifications are as far-reaching as the conceptual ones. A simple atomic-scale interaction informs entire industries, technologies, and scientific fields. Philosophically, Einstein's use of Planck's quantum idea forced scientists to confront a more nuanced reality. Nature was no longer purely continuous, nor entirely deterministic. Energy is quantized. Photons and electrons interact in discrete jumps, and light, the fundamental medium of our perception, cannot be fully understood as just a wave or just a particle. The universe was stranger, more intricate, and more astonishing than anyone had imagined. And it all began with a single, daring insight: that energy comes in packets, and that light itself could be made of them. In essence, Einstein's application of Planck's quantum hypothesis to the photoelectric effect did more than solve a long-standing puzzle. It validated the quantum view of the world, bridged the gap between theory and experiment, and expanded our understanding of light, energy, and matter. It was a moment when mathematics, physics, and observation aligned, revealing a universe in which the smallest packets of energy could illuminate the grandest questions. From the laboratory to the cosmos, from solar cells to quantum computers, the photoelectric effect stands as a testament to the power of Planck's original idea, amplified and clarified by Einstein's genius. The nature of light has fascinated humans for centuries, inspiring theories that ranged from mystical speculations to rigorous scientific inquiry. For centuries, philosophers and scientists debated whether light is a wave, spreading like ripples across water, or a particle, moving like tiny bullets in space. Experiments involving reflection, refraction, diffraction, and interference all seemed to support the wave model. Yet, at the beginning of the 20th century, puzzling phenomena emerged that could not be explained by waves alone. Among these was the photoelectric effect, where light striking a metal surface caused electrons to be ejected, but only if the light had a minimum frequency. The failure of classical wave theory to account for such behavior created a scientific crisis. It was through the application of Planck's revolutionary idea and Einstein's insight that a deeper truth emerged. Light is neither exclusively a wave nor exclusively a particle. It is both, and this dual nature is one of the most profound discoveries of modern physics. Planck had introduced the concept of energy quanta in 1900 to explain Blackbody radiation, suggesting that energy is exchanged in discrete packets. Einstein applied this principle to light itself, proposing that photons, the quanta of light, carry energy proportional to their frequency. When photons strike a metal surface, each photon can transfer its energy to an electron, causing the electron to be emitted. This simple idea accounted for observations that baffled classical physics: the dependence of electron emission on frequency rather than intensity, and the instantaneous ejection of electrons without delay. Experiments confirmed Einstein's predictions, firmly establishing the particle-like behavior of light in these contexts. Yet light had already demonstrated undeniable wave-like behavior. Interference patterns, diffraction through narrow slits, and the spreading of waves across space could not be explained if light were solely a particle. Waves could superpose, creating regions of constructive and destructive interference, whereas particles, following classical intuition, would simply collide or scatter independently. Experiments such as Young's double-slit experiment revealed these wave properties vividly, producing alternating bright and dark fringes that reflected the mathematical nature of wave superposition. These phenomena occurred regularly, reliably, and reproducibly, establishing that light behaves as a wave in many situations. The realization that light exhibits both wave-like and particle-like properties challenged classical intuition. It was no longer possible to think of light exclusively as one or the other. Instead, scientists had to embrace a dual nature. In some experiments, light manifests as a particle. In others, it behaves as a wave. This duality is not a mere philosophical abstraction. It is a measurable, predictable feature of the universe. Photons carry energy and momentum like particles, yet they can interfere and diffract like waves. Depending on the experimental context, different aspects of light's behavior dominate. Nature, it seems, resists simple categorization. The consequences of this duality extend far beyond theoretical curiosity. It became the foundation of quantum mechanics, influencing the behavior of electrons, atoms, and all forms of electromagnetic radiation. Wave-particle duality explains why electrons can diffract like waves, why photons can exhibit interference, and why the quantization of energy is necessary to reconcile observed phenomena. It introduced a new language for describing the universe, one in which certainty and predictability coexist with probability and measurement-dependent outcomes. This principle is essential to understanding atomic structure, chemical bonding, and the operation of modern technology. Practical applications of wave-particle duality abound. Photovoltaic cells rely on the particle aspect of light to convert sunlight into electricity. Lasers exploit the quantum coherence of photons to produce highly concentrated, directional beams. Electron microscopes utilize the wave nature of electrons to resolve structures far smaller than visible light could ever reveal. Even modern quantum computing and secure communication systems depend fundamentally on the dual properties of light, manipulating both its particle and wave characteristics to encode, transmit, and process information. Without the recognition of this duality, the technological world we inhabit today would be impossible. The philosophical implications are equally profound. Classical physics operated under the assumption that reality is deterministic, continuous, and fully observable. Wave-particle duality shattered these assumptions, revealing that the behavior of light and matter depends on how they are observed, and that certain properties cannot be defined simultaneously with arbitrary precision. This principle, later formalized in Heisenberg's uncertainty principle, underscores that at the quantum level, the universe operates under rules that defy classical expectations. Light, in revealing both its wave and particle nature, taught humanity that nature is more subtle, more nuanced, and more astonishing than previously imagined. Experiments continued to reinforce this duality. The photoelectric effect highlighted photons as discrete carriers of energy. Diffraction and interference experiments underscored the continuous wave properties of light. Over time, scientists came to understand that these are not contradictory observations, but complementary aspects of the same reality. Light, like matter, embodies a duality that is fundamental to quantum physics. This duality applies not just to photons, but to electrons, neutrons, atoms, and even larger particles under controlled conditions, demonstrating that wave-particle duality is a universal principle, extending across the microscopic and macroscopic realms. In essence, the confirmation that light acts both like a wave and like a particle marked a turning point in physics. It bridged the gap between classical and quantum understanding, validated Planck's and Einstein's insights, and opened the door to a new era in science. Light, once thought to follow simple, continuous laws, revealed itself as a subtle, dualistic force, guiding physicists toward deeper truths about energy, matter, and the universe itself. It is through this duality that we have come to see the hidden architecture of reality, one that is simultaneously discrete and continuous, predictable and probabilistic, simple and profoundly complex. The story of atomic theory is a story of human curiosity, observation, and the persistent drive to understand the unseen. Long before Planck's revolutionary ideas, scientists had speculated about the existence of atoms, imagining them as indivisible particles that formed the building blocks of matter. Yet, these early models were largely philosophical, lacking rigorous experimental foundation or predictive power. It was Planck's introduction of quantized energy that breathed new life into the study of atomic structure, offering not only a mathematical framework, but also a conceptual lens through which the microscopic world could be understood. By proposing that energy is exchanged in discrete packets, Planck revealed a principle that was fundamentally different from the continuous processes assumed in classical physics. This quantization had immediate implications for understanding atoms. If energy within radiation could only exist in precise, indivisible amounts, it was reasonable to consider that electrons in an atom might also occupy only specific energy levels. The notion of discrete energy levels became a guiding idea for those who sought to explain the stability of atoms and the patterns observed in atomic spectra. Planck's insight suggested that nature itself favored order, that even at the microscopic scale, energy obeyed rules and limits rather than flowing smoothly and without constraint. The hydrogen atom provided the first clear application of these concepts. Spectral lines observed in hydrogen revealed a regular pattern, a series of discrete energies emitted as electrons transitioned between levels. Classical physics could not explain why these lines appeared at specific frequencies, why electrons did not spiral into the nucleus, or why atoms were stable at all. Building on Planck's quantization, Niels Bohr proposed a model in which electrons could only occupy certain allowed orbits, each with a fixed energy. When electrons moved between these orbits, they absorbed or emitted quanta of energy, precisely in accordance with Planck's principle. Suddenly, the behavior of hydrogen, and by extension, all atoms made sense. Planck's abstract idea of energy quanta had been translated into a concrete, visual model of atomic structure. Bohr's model, while groundbreaking, was only the beginning. Planck's insight sparked a wave of theoretical exploration, inspiring physicists to probe deeper into the quantum world. Scientists began to recognize that if energy is quantized, then the dynamics of electrons, the emission of light, and the chemical behavior of atoms all require a fundamentally new approach. Quantum rules replaced the smooth curves of classical orbits with probabilities, discrete levels, and quantized transitions. Atomic models evolved from simple planetary analogies to sophisticated mathematical frameworks capable of predicting the behavior of electrons in multi-electron atoms. Without Planck's initial leap, the recognition that energy could exist in distinct units, these models would have lacked a foundational principle to explain why atoms behaved as they did. Furthermore, Planck's idea helped clarify the connection between light and matter. Photons, each carrying a discrete amount of energy, could interact with electrons in a predictable way. This explained phenomena such as the photoelectric effect, fluorescence, and emission spectra effects that had long puzzled scientists. Atomic models began to integrate these quantum interactions, accounting for how atoms absorbed and emitted light in discrete amounts. The quantized nature of energy provided a unifying thread, linking the properties of individual atoms to observable effects in radiation and spectroscopy. Planck's influence also extended to the development of more advanced atomic theories. As quantum mechanics matured, his constant and the principle of energy, quanta, became essential components in Schrödinger's wave mechanics and Heisenberg's matrix mechanics. These frameworks offered deeper insights into atomic structure, revealing that electrons behave both as particles and waves, existing as probability clouds around the nucleus rather than fixed orbits. Planck's idea served as the conceptual seed from which this entire theoretical edifice grew. Every subsequent refinement of atomic theory, from electron spin to quantum tunneling, traced its lineage back to the recognition that energy is quantized. In practical terms, Planck's insight transformed chemistry and technology. The understanding of atomic structure based on energy quantization allowed scientists to explain chemical bonding, molecular stability, and reaction dynamics. Spectroscopy became a precise tool for identifying elements and compounds, while quantum principles guided the design of semiconductors, lasers, and countless modern devices. The atomic models inspired by Planck's idea bridged the gap between abstract theory and tangible technological application, demonstrating the profound real-world consequences of fundamental physics. Beyond its scientific and practical impact, Planck's contribution also reshaped the philosophical landscape. By showing that energy and atomic behavior are quantized, he challenged classical assumptions about continuity, determinism, and the predictability of nature. Atomic models inspired by his insight emphasized that the microscopic world is governed by rules that differ from everyday intuition. The atom, once imagined as a simple indivisible particle, became a complex system governed by discrete energy levels, wave functions, and probabilistic interactions. An entirely new way of understanding reality. Planck's idea, modest in its initial presentation, thus acted as a catalyst for the development of modern atomic theory. It inspired physicists to move from speculation to rigorous modeling, from observation to prediction, and from classical approximations to quantum precision. The atoms we study today, the spectra we measure, and the technologies we build all owe their foundations to the profound leap that energy is not continuous but quantized. By introducing the concept of discrete energy packets, Planck illuminated the path toward a complete understanding of atomic structure and the fundamental laws that govern matter itself. The early 20th century was a time of extraordinary challenge and discovery in the world of physics. Classical mechanics, with its precise laws and predictable equations, had long seemed sufficient to describe the universe. Planets followed elegant orbits, pendulums swung with perfect regularity, and waves of light and sound could be predicted with confidence. Yet at the smallest scales, the realm of atoms and subatomic particles, these well-established laws began to falter. Experiments revealed behaviors that defied classical expectations. Atoms emitted light in discrete spectral lines, electrons displayed both wave-like and particle-like properties, and energy transfer occurred in ways that continuous equations could not explain. In the midst of this growing crisis, Max Planck introduced a concept so revolutionary that it would ultimately transform all of physics: the quantization of energy. Planck proposed that energy is exchanged not continuously, but in discrete packets, which he called quanta. This idea was initially motivated by the need to solve the Blackbody radiation problem, a discrepancy between theoretical predictions and experimental observations. Classical theory had suggested that the intensity of emitted radiation should increase without limit at high frequencies, leading to the so-called ultraviolet catastrophe. Planck's bold insight that energy is quantized and that each quantum is proportional to the frequency of radiation resolved the crisis. What seemed at first to be a mathematical trick soon revealed itself as a fundamental principle of nature. This principle, simple in its formulation yet profound in its implications, laid the foundation for a new physics, quantum mechanics. Planck's quantum hypothesis was the first step in recognizing that the microscopic world operates under rules distinct from those of everyday experience. By introducing the concept of discrete energy levels, he challenged the classical notion that energy could vary continuously. This departure from classical thinking was not merely a minor adjustment. It demanded a complete reevaluation of fundamental assumptions. Suddenly, atoms were no longer perfectly predictable machines. Electrons could only occupy specific energy levels. Light could behave both as a wave and a particle, and the interactions of matter and radiation followed discrete steps rather than smooth gradients. Planck had opened the door to a universe that was simultaneously structured and probabilistic, precise yet mysterious. The influence of Planck's idea extended rapidly through the work of other pioneering physicists. Albert Einstein, inspired by Planck, applied the concept of quanta to light itself, explaining the photoelectric effect and demonstrating that photons carry energy in discrete packets. Niels Bohr built upon this principle to develop his model of the atom, in which electrons occupy fixed orbits and transition between energy levels by emitting or absorbing quanta. Werner Heisenberg and Erwin Schrödinger later expanded the theory, creating matrix mechanics and wave mechanics to describe the probabilistic behavior of particles and their wave-like properties. In each of these breakthroughs, Planck's original insight served as the foundational spark. Without his recognition of quantization, the subsequent development of quantum mechanics would have lacked its essential principle. Planck's quantum theory also provided a unifying framework for phenomena that had seemed disconnected. The emission and absorption spectra of atoms, the behavior of electrons in metals, the energy levels of molecules, and even the stability of matter itself could now be explained using the same fundamental concept. Quantum mechanics, built upon Planck's principle, demonstrated that the microscopic world obeys universal rules, rules that are discrete, probabilistic, and mathematically elegant. This unity transformed physics from a collection of isolated laws into a coherent theory capable of predicting and explaining the behavior of matter and energy at the smallest scales. The practical impact of Planck's quantum theory is immeasurable. Modern technology relies entirely on the principles that flow from energy quantization. Semiconductors, lasers, superconductors, MRI machines, and quantum computers all operate based on the predictable behavior of discrete energy levels. The understanding of chemical reactions, molecular interactions, and electronic devices hinges on quantum principles derived from Planck's original idea. In effect, the entire infrastructure of contemporary science and technology rests upon the foundation he laid over a century ago. Beyond its technological significance, Planck's theory reshaped our philosophical understanding of the universe. The classical view of a continuous, deterministic reality gave way to a world governed by probabilities, discrete events, and measurement-dependent outcomes. Observations are not simply passive recordings of reality. They interact with the system being observed, and certain aspects of nature are inherently uncertain. Planck's quantization forced scientists to accept that the universe is fundamentally granular at its core, and that continuity is an approximation, not a fundamental truth. The legacy of Planck's quantum theory is therefore both practical and conceptual. It provided the tools to navigate the atomic and subatomic realms, giving rise to an era of physics that continues to evolve today. It challenged established beliefs, inspired new generations of thinkers, and opened the door to technologies that were unimaginable in Planck's own time. His insight that energy is quantized and that nature operates in discrete packets was the key that unlocked the quantum universe. Ultimately, Planck's quantum theory laid the foundation for all of modern quantum mechanics. It transformed physics from a classical, predictable framework into a dynamic, probabilistic, and profoundly more accurate understanding of the microscopic world. From the behavior of photons and electrons to the complex interactions of molecules and materials, every aspect of quantum physics traces its origin to this foundational idea. Planck's discovery remains a testament to the power of insight, the courage to challenge assumptions, and the enduring impact of a single, revolutionary idea on the course of science. Before the dawn of quantum theory, the world of physics seemed complete, governed by elegant laws that could explain the motion of planets, the flow of fluids, and the propagation of light. Classical mechanics, thermodynamics, and Maxwell's equations painted a picture of a universe that was continuous, predictable, and comprehensible. Energy was considered a smooth, unbroken quantity, flowing seamlessly through systems. Matter, too, was treated as a tangible, solid entity, composed of particles obeying deterministic rules. Yet, as experiments probed the microscopic world, cracks began to appear in this classical framework. Radiation, atomic spectra, and the behavior of electrons defied explanation. The universe, it seemed, was more complex, more subtle, and more astonishing than anyone had imagined. It was Max Planck who first offered a glimpse into this hidden structure, introducing the idea that energy is quantized, emitted, and absorbed in discrete packets known as quanta. This simple yet radical idea would revolutionize our understanding of energy and matter, reshaping physics forever. The quantization of energy immediately challenged the classical world view. Instead of energy varying smoothly, Planck's theory suggested that energy changes occur in steps, like climbing the rungs of a ladder rather than ascending a ramp. This was not a minor correction, it was a fundamental rethinking of how the universe operates at its most basic level. Suddenly, the behaviors that had puzzled scientists why Blackbody radiation did not increase infinitely at high frequencies, why electrons in atoms did not collapse into the nucleus, and why light sometimes behaves like a particle, could all be understood as manifestations of discrete energy interactions. The very concept of energy was transformed from a continuous, infinitely divisible quantity into a granular, quantized entity, revealing that nature has limits at the smallest scales. Quantum theory expanded this revolutionary perspective from energy to matter itself. Electrons, once imagined as tiny planets orbiting a nucleus, were understood to occupy discrete energy levels, transitioning between states only by absorbing or emitting quanta. Atoms and molecules could no longer be described purely in terms of classical orbits or trajectories. Their behavior became inherently probabilistic, described by wave functions, probabilities, and the uncertainty principle. Matter was no longer a passive, predictable substance. It was dynamic, interacting with energy in ways that were quantized, non-intuitive, and deeply interconnected with the principles of light and radiation. This view appended centuries of classical thinking, revealing that the microscopic world operates under a fundamentally different set of rules than the macroscopic world we observe daily. The revolution was not merely theoretical. quantum theory provided the framework for understanding phenomena that classical physics could not explain. The photoelectric effect demonstrated that light interacts with matter in discrete packets, confirming the particle-like behavior of photons. Spectral lines in atoms and molecules, once mysterious, were now predictable through the quantization of energy levels. Quantum tunneling explained processes such as radioactive decay and nuclear fusion, revealing mechanisms by which particles could traverse barriers that classical physics deemed impossible. In every instance, energy and matter behaved according to principles that were discrete, probabilistic, and intertwined in ways that classical laws had never anticipated. This transformation had profound implications for technology and daily life. Quantum mechanics, built upon Planck's foundational ideas, led directly to semiconductors, transistors, and modern electronics. Lasers, magnetic resonance imaging, and solar panels rely on the quantized interactions of energy and matter. Even our understanding of chemistry, the way atoms bond, molecules form, and reactions occur, is governed by quantum principles. Without Planck's insight, the predictive power of modern science, the technological innovations that define contemporary civilization, and the precise control over matter and energy at microscopic scales would have been impossible. Quantum theory turned the abstract behavior of electrons and photons into tangible applications that shape our everyday existence. Beyond practical applications, quantum theory transformed our conceptual understanding of the universe. Energy is not continuous, it exists in packets. Matter is not a collection of predictable particles, it is probabilistic, wave-like, and inherently interconnected with energy. Observers cannot measure certain properties simultaneously with absolute precision, revealing an inherent uncertainty in nature. Classical determinism gave way to a new framework where probabilities and discrete events govern the microscopic world. This intellectual shift reshaped physics, philosophy, and our perception of reality itself, teaching humanity that the universe is more nuanced, more surprising, and more intricate than classical intuition had suggested. Quantum theory also created a unified understanding of phenomena previously considered disparate. The interaction of light with matter, the emission and absorption of radiation, the stability of atoms, and the mechanisms of chemical bonding all emerged as consequences of the same underlying principles. Energy and matter were no longer separate realms. They were facets of a single, interconnected quantum reality. Planck's simple proposal, that energy is quantized, was the keystone of this structure, providing the conceptual bridge that allowed physicists to understand the microscopic world as a coherent, unified system. The revolution continues to evolve. Quantum theory has inspired further discoveries such as quantum entanglement, superposition, and the development of quantum computing. It has challenged our intuition, extended the boundaries of knowledge, and deepened our appreciation for the subtle complexity of nature. By demonstrating that energy and matter behave in discrete, probabilistic, and interconnected ways, quantum theory reshaped both science and philosophy, altering the very lens through which we observe reality. In essence, the introduction of quantum theory marked a profound turning point in our understanding of energy and matter. It transformed abstract mathematical ideas into a precise description of reality, revealed the discrete and probabilistic nature of the microscopic world, and laid the groundwork for technological innovation and scientific exploration. The universe, as Planck, Einstein, and their successors revealed, is not smooth and predictable at its core. It is quantized, dynamic, and astonishingly intricate. The revolution initiated by quantum theory forever changed the way we perceive, study, and interact with the fundamental building blocks of nature, illuminating a world far richer and more mysterious than classical physics could have imagined. Max Planck's name is forever etched in the annals of science as the man who opened the door to the quantum world, a door that would fundamentally alter humanity's understanding of the universe. His legacy is not only one of brilliant insight, but also of the courage to challenge prevailing assumptions, to venture into uncharted territory, and to illuminate truths that were invisible to classical physics. Planck lived in an era when Newtonian mechanics and classical electromagnetism seemed sufficient to explain the workings of nature. Yet he sensed that, at the smallest scales, the universe was more subtle, more intricate, and more mysterious than previously imagined. Through his relentless curiosity, meticulous calculations, and bold hypotheses, Planck introduced the revolutionary concept of quantized energy, laying the foundation for all of modern quantum mechanics. Planck's journey began with a seemingly technical problem: Blackbody radiation. Classical physics predicted that an idealized object absorbing and emitting radiation would emit infinite energy at high frequencies, a contradiction known as the ultraviolet catastrophe. Scientists were baffled, and the laws of physics appeared inadequate. Planck approached this problem with characteristic precision and care, analyzing experimental data with patience and rigor. In the course of his investigations, he discovered a pattern that defied classical understanding. To reconcile theory with observation, he proposed that energy is not emitted or absorbed continuously, as previously thought, but in discrete packets called quanta. Each quantum is proportional to the frequency of radiation, introducing the now famous constant h, Planck's constant, which serves as a fundamental bridge between energy and frequency. This seemingly simple proposal would reverberate through physics, chemistry, and technology for generations to come. Planck himself was cautious about the full implications of his discovery. At first, he regarded quantization primarily as a mathematical device, a tool to make his equations match experimental results. He did not immediately embrace the notion that energy itself was fundamentally discrete. Despite his initial skepticism, the conceptual leap he had made could not be ignored. Soon, other scientists recognized the profound significance of his work. Albert Einstein applied Planck's quantum hypothesis to explain the photoelectric effect. Niels Bohr incorporated it into his atomic model, and a new generation of physicists began to develop the full framework of quantum mechanics. Planck's insight had set the stage for a scientific revolution, even before he fully realized the depth of his own contribution. The influence of Planck's work cannot be overstated. By introducing the idea that energy is quantized, he provided a principle that unified previously inexplicable phenomena. Spectral lines, atomic transitions, the behavior of electrons, and the interaction of light with matter all became intelligible within the quantum framework. His constant, h, became a fundamental cornerstone of physics, appearing in equations governing everything from atomic structure to the behavior of particles at subatomic scales. Planck's work demonstrated that the universe at its smallest scales is neither continuous nor fully deterministic, but operates according to discrete, quantized steps. This insight forever changed the way scientists approach the microscopic world. Beyond his scientific achievements, Planck's legacy also reflects his character. He was a man of humility, integrity, and perseverance. He pursued truth patiently, guided by a deep respect for empirical evidence and logical reasoning. He did not seek to overturn the world of classical physics for fame or recognition. Yet his discovery ultimately became the catalyst for one of the most profound transformations in human understanding. He mentored, inspired, and influenced countless physicists, setting the stage for the golden age of quantum mechanics. His approach combined precision, creativity, and caution, showing that groundbreaking ideas often emerge from careful thought, not impulsive conjecture. Planck's legacy extends beyond theoretical physics into practical applications that define modern life. Quantum theory underpins technologies that were unimaginable in his own time. Semiconductors and transistors that power computers and smartphones, lasers that revolutionize medicine and communications, magnetic resonance imaging that allows us to see inside the human body, and solar cells that harness energy from the sun. Every innovation in electronics, photonics, and quantum computing traces its lineage back to Planck's original insight. His work bridged the gap between abstract theory and practical reality, demonstrating the profound interplay between fundamental science and technological progress. Philosophically, Planck reshaped humanity's understanding of nature. The classical worldview, which treated energy as continuous and matter as predictable, was replaced by a quantum vision in which the microscopic universe is probabilistic, discrete, and interconnected. Observers discovered that energy exists in indivisible units, particles behave as waves, and the very act of measurement affects outcomes. Planck's quantum hypothesis challenged centuries of assumptions, teaching that the universe is more subtle, more intricate, and more surprising than intuition alone can reveal. By revealing this hidden order, he transformed not only physics, but also the way humans perceive reality itself. Ultimately, Max Planck is considered the father of quantum theory because he provided the initial spark that ignited a scientific revolution. Without his introduction of energy quanta, the discoveries of Einstein, Bohr, Heisenberg, Schrödinger, and countless others would have lacked a foundation. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, owes its existence to Planck's insight. His work demonstrates that even a single, carefully reasoned idea can reshape human knowledge, open doors to new technologies, and alter the trajectory of science forever. Max Planck's legacy endures not only in the constants, equations, and experiments that define physics, but in the spirit of curiosity, courage, and careful reasoning that he embodied. He showed that the universe contains hidden rules, that the smallest scales reveal profound truths, and that careful observation combined with bold imagination can uncover the mysteries of existence. He laid the foundation for the quantum era, and through his work, humanity gained a new vision of the universe, one in which energy and matter dance in discrete, measurable steps, revealing a cosmos far richer and more extraordinary than anyone had ever imagined.